Hello and welcome back to Math Class in Session. Yet more optimization problems. Let's review the steps, get an expression for the function you're trying to maximize or minimize and get it into just one variable, set the derivative equal to 0 and solve for the variable, investigate the critical points and the boundary points. Now the boundary points are, well, sometimes not necessary to evaluate in a word problems, and sometimes they are. You have to use your judgment on that. Prime it, zero it, and solve it is a policy to follow. Let's get started. Example, find the exact volume of the largest cylinder that can be inscribed into a sphere of radius 5 meters. Inscribed means fit inside so that the corners of the cylinder are touching the sphere. Solution. You can't learn to swim by watching somebody swim. This is a fact. And it applies here and to all of these videos. I strongly suggest that you pause the video and try the problem or the problems as you encounter them on your own on a blank sheet of paper and take your best shot at trying to solve it. And then maybe follow the video and see how you did. Solution. Draw a diagram. This is a cylinder inscribed into a sphere. Now it could be a pipe. I mean, if we were to take this part of the cylinder and slide it up and make it smaller so that it still fits inside the sphere, it could be a long tube like a pipe, or we could drag this down here and make it almost like a hamburger patty or something, like a wide, thin cylinder. And the question is, which cylinder has the maximum volume? And what is that exact volume? So we do the math. Let P be the center of both the cylinder and the circle, a point. So if we were to, say, draw a line from P over to the surface of the sphere, that would have to be 5 meters. And then we're interested in the height of this cylinder as well as its radius so that we can start adding to our diagram here. We have the radius of the, not the sphere, but the radius of the cylinder, and half of its height will be from its middle to its top. So this would be h over 2. And from Pythagoras we get 25 equals r squared plus h squared over 4. And from this it follows that r squared is 100 minus h squared over 4. And the volume of the cylinder is pi r squared h. But we've developed an expression for r squared, so here's a formula for the function we're trying to maximize, but there's too many variables, so we'll take this r squared and replace. And simplifying this a bit by multiplying the pi into the numerator and this h into this numerator, and we end up with an expression in one variable for the thing we're trying to maximize or minimize. From here on out, it's just the technical work. Priming. Since it's over 4, we can just leave it over 4 and differentiate the numerator. Setting it equal to 0 means just the numerator equals 0. And we've got to solve this for h, so we can drag the term that has the h squared and divide by 3 pi, take square root both sides, and we have found h, the height of the cylinder that maximizes volume. Now we want to find the exact volume, so we'll have to take this h and plug it into our volume expression. But we might make things easier by factoring out pi over 4 from this volume expression and then subbing in h being root 100 over 3, so plugging it in there and there. Now when we take the cube of a root, well, first we could square it. That would leave 100 over 3 times the root again. So this would be, this part of this expression is h cubed And looking and thinking some more, we can see that 100 will factor out, and 100 over 4 is 25. So we have our 25 pi on the outside with this 100 factored out and divided by 4. And now looking inside these brackets, we can say we have 1 whole root minus 1/3 of that same root. So that must leave behind just 2/3 of that same root. Processing further, we see the square root of 100 is 10, and 10 times 2 is 20. And 20 times 25 is, well, 2 times 25 is 50. So 500 pi over 3 root 3. And some might want to rationalize the denominator. And we have our maximum volume, 500 pi root 3 over 9 cubic meters. As always, pause the video, dwell on the math. Another example, find the maximum area of a rectangle that can be inscribed into an ellipse with an equation for the ellipse being x squared plus 4y squared equals 4 with its sides parallel to the axes as shown. Solution, let P be the point shown. So we could let that point be P. And if there's an origin here, then this must be x displaced to the right of the origin, and then y displaced upwards, but we know that y equals square root 4 minus x squared over 4. Because when we solve this for y, that's what we get. Dragging the x squared and dividing by 4 and taking the square root, we have y equals the square root of 4 minus x squared all over 4. Area of a rectangle is length times width, so area of this particular rectangle will be length. Now the length is from the middle to the edge is x, so the length of this rectangle must be this 2x here. Meanwhile, the width of the rectangle is from the x-axis all the way to the top and all the way to the bottom, so there's 2 y's, so there'll be 2 of those. And thinking further, the square root of this numerator over the square root of this denominator means the denominator becomes root 4, which is 2, and it cancels off this 2, leaving behind square root 4 minus x squared, which we could put into the base of a power raised to the 1/2 like this. Why? Because we're about to differentiate. Here we go, differentiating a product of functions of x. First thing prime times the second thing plus the second thing primed, which is 1/2 times all this to the minus 1/2 times minus 2x times the first thing. And simplifying our derivative will be half of 2 will cancel. And so this will be minus 2x squared. And I put the root of 4 minus x squared into the denominator under a root sign as is appropriate. Continuing, we have 2 terms in our derivative, which is equated to 0. 2 terms. We could take one of those terms and drag it across and join it with the 0. So now we have a term equals a term. And we note that the 2's will cancel off of both sides. And if we multiply this root over with this root, we can toss away the root signs, and we get x squared equals 4 minus x squared. Solving for x squared, we get 2x squared equals 4, so x squared equals 2, and x equals root 2. A couple of steps there mentally. Dragging the x squared makes 2x squared, divide by 2, you got 2, x squared equals 2, so x equals root 2. And a little bit of a challenge here. Let's take this root 2 and see if we can plug it in here and state the area just by looking. Root 2 squared, that's 2. 4 minus 2, that's 2. Under a 1/2, that's root 2. And x again is root 2 times root 2 is 2, and 2 times 2. It follows that the area is 4 square units. You can write some of that out if it helps. A last example, the fuel cost per hour for running a ship is approximately 1/2 the cube of the speed measured in knots, plus additional fixed costs of $216 per hour. Find the most economical speed to run the ship for a trip which is 500 miles long, nautical miles. Couple of words here. Knots means nautical miles per hour. The big M means nautical miles. A nautical mile is 6/5 of a regular mile. So if you're going, say, 10 knots, you're going a little faster than 10 miles an hour. Actually, 6/5 of 10 miles an hour. Okay. Solutions start by defining some variables. Let's let t represent the total time that this trip is going to take in hours. And let's let s represent the speed that the ship will go in knots, nautical miles per hour. And now we have to build an expression. C of s, the cost for a given speed. Because the question is, find the most economical speed to run the ship, so we want to minimize cost. Cost for a given speed is, well, let's add up the costs here. $216 per hour. So it'll be 216 for every t, t being the total time in hours, plus 1/2 the cube of the speed every hour. So this is the cube of the speed over 2, so 1/2 the cube of the speed every hour, so that's why it's multiplied by t. And so we have our expression for cost for a given speed. The problem is there's 2 variables. And our second step is get the expression into just one variable. So we would like to get rid of this t because we want cost for a given speed. So if only we had a relationship between time and speed, and we do. Time is distance over speed. And the distance we know is 500 nautical miles. So the time is 500 over the speed. So every time we see this t, we can replace it with distance over speed, so 500 over s. Doing a little bit of math here, t I just simply replace with 500 over s. This t is 500 over s as well. That's why a 2s showed up on the bottom and a 500 showed up on the top. Now we have c of s in just one variable. Simplifying, multiplying out this top, 500 divided by 2 is 250. Put this s up here under a negative exponent. Why? Because it's time to differentiate. That's the next step. C prime of s minus 1 times all of this to the minus 2 plus 2 times 250 is 500s. Prime it, zero it, set it equal to 0. Now, if this is 0, this negative term can be pulled across this equal sign and made positive. And so we've got a term equals a term, kind of like the last example. And we'll multiply the s squared over to join it up with that s squared. To join it up with that s to make an s cubed. And divide both sides by 500. Do it on a calculator if necessary. Take cube root both sides, and we have our speed, s equals 6. And at s equals 6, we've minimized the cost. The most economical speed is 6 knots.